The next two of the four gas variables to look at actually are called Charles' law, and we're going to look at volume and temperature. So a few things. What do you think if I increase the temperature, what do you think should happen to the volume? Assuming that we're going to try to hold pressure constant and keep the number of moles constant. Well, the volume will go up because of the kinetic energy, increased kinetic energy of your gas particles. So that is totally Charles' law. Now, one thing about it though is our temperature needs to be in units of absolute temperature. So what scale do we use for absolute temperature? Yep, that's the Kelvin scale. So let's see if I can clear these. I think I can. Yeah. All right, so here we go. Welcome to Charles' law. So if one goes up, the other goes up. We call that a directly proportional relationship. So they are directly proportional, so we simply use the proportionality symbol. Okay, so we said that actually we can replace, how do we say this? If you have a proportionality symbol and you want to put an equal sign there, you can do that as long as you introduce what we call a constant. So if they are directly proportional, and if we introduce a constant, we would say that the ratio of volume and temperature remains constant. So that's to say if volume goes up, temperature must go up so that mathematically the ratio remains the same number. If volume goes down, temperature will go down. Okay, so that it holds that same constant. So I've got some examples for you coming up. This is David Letterman used to do it a lot with, I think, liquid nitrogen. Liquid nitrogen is very cold, and that's actually what we have here. That's nitrogen in its liquid state. They got it that way by making it very cold. So that's not the point here. What we're going to do is these balloons actually have little gas particles. Those are our gas particles of interest. So as we cool down the temperature, okay, we would expect what? The volume to also decrease. And that's what's happening here. They kind of remind me like if you get, I think this is the way it works, if you get ants in the mail, sometimes they will be, maybe in the wintertime, they will be nice and lethargic because they're nice and cooled down. Okay, but anyway, so these little gas particles are hugging each other. So this is the small volume. And the cool thing over here is if we go and liquid nitrogen, you had to be very careful. Here we're using, I think I'd be even more careful than this, but we're carefully taking these back out, and guess what happens? As we increase the temperature, what happens to the volume? Volume increases, and that's what you're seeing here. They're alive again. Okay, so that's Charles' law. Another real common sort of example is this right here is a heat source. So as we increase the temperature, we're going to increase the volume. And actually that gives us our, your balloon then, the buoyancy it needs to rise. So hot air balloons. So what this says is if we go ahead and take this is our gas, and notice what we're going to do here. I'm going to go backwards. I'm going to go from right back to left again. I'm going to cool it down. It has a smaller volume. I'm going to cool it down. It has a smaller volume, smaller volume. This is my volume going down, smaller volume, smaller volume. So at some point it seems like I should have a cold enough temperature so that actually the volume is what? 0. Okay, so that 0 volume actually intersects with a temperature of 0 Kelvin, which is negative 273 degrees Celsius. So that's kind of fun. This is actually kind of showing you that extrapolating down, a cooler temperature, smaller volume, a cooler temperature, smaller volume, cooler temperature, smaller volume. Okay, go back and you're going to hit 0 volume at negative 273 Celsius, which is equal to 0 Kelvin, or absolute 0. Now, the catch here is that, and we kind of talked about ideal gas behavior, if you get too cold, basically your gas particles begin behaving non-ideally. So that's kind of what you're up against there, but it's true. So let's see what this little video does for us.
Temperature and volume are directly related. As heat is added to a sealed syringe, the volume of the air in the syringe increases. A plot of gas temperature and volume demonstrates that the relationship between them is linear. If we extrapolate the line down to a temperature of absolute zero, in principle, the gas has no volume.
Isn't that cool? No pun intended. Let's see if I can. Okay. So one last slide before I move on. Now, when we say that, see, temperature over volume is equal to some constant, or volume over temperature is equal to some constant, it's the same thing. The temperature in that case has to be in units of kelvins. If you're in units of Celsius or heaven forbid Fahrenheit, it doesn't make sense. So whenever we work gas problems, our temperature always has to be in units of Kelvin.